we're going to discuss partial fraction decomposition. First, let me just have you consider, I'm not going to go through the process, but consider if we're adding a couple of fractions together. For instance, if we're adding 8 over x plus 1, in fact, let's say we're subtracting. Subtract the fraction 5 over x minus 4. Well, we would go through a process by getting a common denominator and then multiplying out appropriately the numerators and doing the subtraction. And you can verify this. This is not really so much the issue here. I just want to make the point. When we do this, we would get 3x minus 37 divided by x plus 1 times x minus 4. That ends up being the lowest common denominator. And we can multiply that out. Okay. Well, so we're going from a subtraction of a couple or more fractions. We could have more fractions, and we get a single fraction. Well, what partial fraction decomposition is, so we understand what it is going the other way. We're going to take one fraction, okay, we're going to take something like 3x minus 37 over, and maybe if it were multiplied out, we would have, what, x squared minus 3x minus 4. We're going to take that fraction and we're going to decompose it. In other words, we're going to undo the subtraction. We're going to find out that if we break that or decompose it into a sum or difference of several fractions, this would be what the fractions are. So we're going this direction rather than the other direction in the first example. That's what partial fraction decomposition is. And the reason we do this, particularly in calculus when we're integrating, the one fraction's hard to deal with, but the two simple fractions on the right side are easy to deal with. So that's the purpose. Now, let me also make a note here. Partial fraction decomposition, what we're talking about here, can only be done on proper rational functions. Partial fraction decomposition can only be accomplished on proper rational functions. The process, at least, that we're going to talk about. Well, first, what is a rational function? A rational function is a function defined as a polynomial divided by a polynomial. So to have a rational function, both of these expressions in the numerator and denominator are polynomials. Now, in the example, well, we'll leave it at that, polynomials. To be proper means that the degree of the numerator, that is of p of x, is smaller than the degree of the denominator, than that of q of x. Okay, so as an example, this would be a proper fraction. In fact, what we'd written there is a proper fraction. 3x minus 37 divided by x squared minus 3x minus 4. The degree of the denominator is 2, and the degree of the numerator is 1. So when the degree of the numerator is smaller than the degree of the denominator, it's a proper fraction. And of course, there would be many other examples. That's just an example of one. And it's kind of like what a proper fraction would be when you're talking about numeric fractions. A proper fraction is where the numerator is smaller than the denominator. That is, you can't divide into the numerator any whole number of times or big. You have some fraction that's actually less than 1. The numerator is smaller than the denominator. An improper fraction, when we're talking about rational functions, would be an example like 3x squared minus 2 over x squared minus 1. And the reason that this is improper is the degrees are the same. And remember, to be proper, the degree of the numerator has to be smaller. And of course, another example, straightforward example, would be something like 3x to the 4th plus x squared minus 2, all divided by 5x squared plus 3. Well, here clearly the numerator degree is larger than the denominator degree. So those are improper fractions. In other words, we can't decompose these. We can't decompose using the method that we're using. We can't do it. Okay. Well, let's take this example. We already know the result, but let's take this example on the next page and let's decompose it to see what the process is. And then we'll look at all of the other variables or variations of things that we can or can't do. Okay, as we're just talking about, we're to decompose the fraction 3x minus 37 over x squared minus 3x minus 4. And so the first thing we do is factor the denominator. So we're going to take our fraction, we're going to factor the denominator, and here it factors as x plus 1 times x minus 4. Okay. Now, the next step after we factor the denominator is to understand what the decomposition is going to look like. Not what all the numbers involved are, but what the decomposition is going to look like. And that's the biggest issue all the way through. Once we understand what the decomposition will look like, then we can go further. Well, what I will tell you is that because we happen to already know, but because we have two factors and they're both linear factors to the first power, we're going to have a fraction that has, in each case, a fraction that has a factor of the denominator as the denominator of the fraction. So we know it's going to look like something over x plus 1 plus something over x minus 4. That's what it's going to look like. And I'll be more specific here later on. Now, we have to decide what the numerator is going to look like. And what it boils down to is we have to decide the degree of the numerator. That is, whether it's going to have no x values, if it's going to have an x to the first in it, if it's going to have an x to the second, and so on. We need to know the degree of the numerator. And the degree of the numerator will be 1 less than the degree of the denominator. Well, the degree, if we take this fraction, the degree of the denominator is 1. And so the numerator is going to be 1 degree less. The degree of the numerator is going to be the degree of the denominator minus 1. And so in this case, that's 1 minus 1, or 0. Well, what does 0 degree mean? It means it has an x power to the 0, an x to the 0 power. That's the degree. But x to the 0 power, well, let's write it this way. Some number times x to the 0 power. But x to the 0 power is just 1. And so it just ends up being a constant. In other words, a constant is of degree 1. And so if we know, of degree 0, pardon me. So if the denominator is degree 1, the only thing the numerator can look like is a constant number, because it's degree 0. And then we look at the next fraction, and we recognize also the degree of the denominator is 1. So that tells us the numerator has to be degree 0, which means it has to be a constant. So that's what it's going to look like. Now, so the next job is just determine what the A value and the B value is. We can look back and see, but how do we do that in general? Well, we take this identity, we take this equation, this identity, and we get rid of the denominator on the left side by multiplying both sides of the fraction by the denominator. Now, I'm not going to do this over and over. We're going to do some of this in our head later on, but we're going to multiply both sides of this equation, this identity, by the denominator that is on the left side. And of course, on the left side, we'll get complete cancellation, won't we? But we also have to multiply the right side, which means we have to multiply both of the existing fractions over here by that denominator, x plus 1 times x minus 4. Okay, times our last fraction. I see this takes up the whole width of the page, doesn't it? Now, of course, on the left side, obviously, we get complete cancellation, so we're left with just 3x minus 37. Okay. On the right side, in the first fraction, we get the x plus 1's canceling, so we're left with an x minus 4 times an a. And in the second term, we get the x minus 4's canceling, and so we're left with an x plus 1 times ab. Now, here's what we're going to do. Let me take a little break here. I hope that I'll have enough space when I take this away. Here's what we're going to do. We're going to have a polynomial on each side. And so let me just get you to think about this generally. If on one side we had 2x squared plus 3x minus 5 is equal to some, let me call it, for this sake here, let me call it ax squared plus 3x plus c. And we knew those two polynomials were equal. And the question is, well, what is a and what is c? What are the values of a and c? Those are the only two pieces we don't have information about. Well, what we end up doing is we compare them and say if these two sides are the same, then on the left side, the coefficient of x squared is 2, but on the right side, the coefficient of x squared is a, so that tells us that the a value actually has to be 2. And likewise, let's see, the 3x and the 3x match up, so there's no issue there, but we come to the constant on the left side, which is -5, and the only term over here that doesn't involve an x is c. So c must be the constant, and so c has a value of -5. And that's really the whole crux of what we're going to do next. So the way we approach this is we need to rewrite the right side. We need to multiply the a's and b's out and combine terms so we see the coefficients of x and the constant terms all combined. So above, I'm going to multiply with the a with the x, and I'm going to put it in front because a is a constant. And I'm going to multiply the a with the -4, and so I'm going to say minus 4a. And then over here with the second term, b times x, I'm going to write as bx, and then plus b times 1, which is just b. Now, as I continue here, I have 3x minus 37. On the right side, I have two terms involving x. That's like a 7x and a plus 4x. We add the coefficients. That is, we add the a and the b. Those are the coefficient of x. And, of course, that's times x. Now, I'm going to put a plus sign here. The other two terms, the minus 4a and the plus b, aren't associated with x's, so we don't have them times any x's. So I'm going to say what we have left over is plus a -4a and a plus b. And now we compare the left with the right. On the right side, the coefficient of x is a 3. The left side. On the right side, the coefficient of x is an a plus b. So that tells us that a plus b must be the same number as 3. They're both the coefficient of x. On the left side, the constant term is -37. on the right side, the term that doesn't involve x is negative 4a plus b. So that tells us negative 4a plus b must be equal to that negative 37 value. Now, we have that information. The next thing we're worried about, though, is we have two equations and two unknowns. That's called a system of equations, isn't it? And we need to solve this system of equations to calculate a and b. And we could do it one of several ways. And what I'm seeing here is in this first equation, I could actually solve that for b. I could say, oh, well, look, b is 3 minus a. Okay? And then in the second equation, I could use that information. I could put this 3 minus a in the place of the b that I have here. So I would have negative 4a plus my b value, which is 3 minus a, is equal to negative 37. And from there, I'm on my way. Because this would, as I combine my terms, I'd have negative 5a plus 3 is negative 37. And when I subtract 3 on both sides, I would have negative 5a is equal to negative 40. And when I divide on both sides by negative 5, I would have a is equal to 8. Now, once I know my a value, I could go back to this equation that says b is equal to 3 minus a. And I could say b is equal to 3 minus the a value I have, which is 8, or b is equal to negative 5. So if we look at this decomposition that we knew it was going to look like, what we have is 3x minus 37 divided by x squared minus 3x minus 4, but we factored it already, is equal to a over x plus 1. Well, a is 8 plus b over x minus 4. But b is negative 5, so negative 5 over x minus 4. And then the only thing that we might do differently is we might rewrite this so we say subtract instead of plus. That is, we could say this is 8 over x plus 1, subtract 5 over x minus 4. And that's what we knew that we were going to get, but now we see the process to go through. So now it can get more difficult than what we've done here, but we first have to understand the circumstances of how we decide. It's this first step here. What is the decomposition going to look like? And after we know what the decomposition is going to look like, we go through the other steps. So I'll begin to talk about that on the next page. So how do we determine the format of the decomposition? And here's, let me in fact rewrite, rules for decomposition. Well, the first thing we do is factor the denominator completely. Whatever completely means. I'll discuss that more in a moment. Now, here's the next question. We look factor by factor at the factors of the denominator. So, for instance, if we have a factor in the denominator, okay, and I'm going to break it down this way. First, we're going to talk about if we have a factor that is linear, a linear factor. So that means it's some number times x plus some number. Now, the a could be 1, the a could be 10, the a could be negative 3, the b could be 0. The a can't be 0, otherwise we wouldn't have a linear factor. So it's of the form ax plus b. If we have a factor that's of the form ax plus b, then the term, for every factor in the denominator of the fraction, we have a term in the partial fraction decomposition. So this factor is associated with a term in the decomposition, it looks like this. We just saw that. It's a constant over that factor. The numerator of the term in the decomposition is of degree 1 less than the degree of the factor that's in the denominator, okay, the denominator itself. Now, the next possibility is we have a factor in the denominator of the original function that we call a repeated factor, okay? So a repeated linear factor that's in the denominator of the original function, okay, what we're trying to decompose. Well, that means is when we get it all factored, we have a linear factor that occurs more than once. When we factor it, we have that factor occur more than once. In other words, we can write it as that factor to a power k. That's k if you can't read it. When we have that situation, then we will have multiple terms associated with this one single factor that's of a power greater than 1. Okay, so here's what we would do. We would have a term in the decomposition that had the factor ax plus b to the first power. And then we would have another fraction that had the factor ax plus b to the second power. And we would continue adding these factors until we finally got up to a denominator, ax plus b to the power k. So for instance, if k was 3, we'd have ax plus b to the first, ax plus b to the second, ax plus b to the third. We'd have 1 for each of those repeated factor amounts. Now, what would the what would the numerators look like? Well, in each case, the factor involved is ax plus b. And since that's a first degree factor, then our numerator would just be a constant. Now, when we look at the second fraction, ax plus b squared, if we were to multiply it out, we would have a squared term. But the factor involved is ax plus b. It's just to the second power. So since the factor ax plus b is to the first power, then maybe I should have called this a sub 1, and maybe I should call this one a sub 2. Okay. Then we'll have a constant, of course, for the numerator of that fraction. And all the way to the end, we would have also a constant numerator because the factor involved is ax plus b. Although it's to multiple powers, it's still just ax plus b. Okay. Well, sometimes we have a factor in the denominator of the form ax squared plus bx plus c that we call an irreducible quadratic. Now, what irreducible quadratic means, I mean, from pre-calculus, we learned that every polynomial can be factored into linear factors. But sometimes to do that, we have to use irrational numbers like square roots, or we have to use complex numbers, that involve I. Well, irreducible means that we can't factor it using the normal methods. That means we can't factor it unless we use something besides integers or rational numbers in the factorization. So something, for instance, like x squared plus x plus 1, we can't factor that in a normal way. That's an irreducible quadratic. Or even x squared plus 5. We can't factor that without involving complex numbers. And so that's an irreducible quadratic. Okay. Well, when we have an irreducible quadratic factor in the denominator of the original fraction, it's going to have a term in the decomposition that has that factor as the denominator. So that's going to end up, that factor is going to end up being a denominator of a term. Now this time though, the denominator is of second degree. And so the numerator is going to be of first degree. Remember, it's 1 degree less. And first degree means it has an x value. So what we would say is that it's some number times an x plus some constant times a b. I mean, 3x plus 5 is a linear factor, isn't it? And we may find out that the b is 0. We might find that out, but we don't know in advance. So if we have an irreducible quadratic factor of the original fraction, the decomposition is going to have a fraction that has that irreducible quadratic as a denominator. One last possibility is that we have a repeated irreducible quadratic factor. That is, when we get everything factored, we have an irreducible quadratic to a power that's in the denominator of the original fraction. So this is a repeated irreducible quadratic factor. Well, it follows the same pattern as the repeated linear factor. What we're going to have is we're going to have this irreducible quadratic factor appear as a denominator from the original power. I'm really out of room, aren't I? From the power 1 up to the power that we have, so power 1 and power 2, and then it would continue, dot, 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 until we got to the full complement of powers. And I really feel bad that I'm running out of room here, but up to whatever the k power is that we started with. But in each case, we have a linear factor in the numerator. So each of these would look something like a linear factor in the numerator. We don't run into this real frequently, but at least it's nice to know how we would deal with each situation. That's kind of messy to read. Probably the next thing for us to do is look at 2 or 3 more examples. And we'll begin those on the next page. Well, here we're supposed to decompose the rational function that you see there, 3x squared minus 7x minus 2, divided by x cubed minus x. And of course, we may have already forgotten, the only time we can do this if it's a proper fraction. And this is because the numerator degree is 2 and the denominator degree is 3. Okay, so the next thing we worry about is factoring the denominator. Okay, so I'm looking at the denominator, x cubed minus x, and of course, that's x times x squared minus 1, and of course, that's x times x plus 1 times x minus 1. Okay, so we'll rewrite the fraction as 3x squared minus 7x minus 2, divided by the factored form of the denominator, x times x plus 1 times x minus 1. Now, we see that we have 3 different factors in the denominator. So we're going to have 3 different fractions in the decomposition. And the first factor in the denominator is just simply x. And so the first denominator is going to be x. The second factor in the denominator is x plus 1. So we're going to have a fraction that has the denominator x plus 1. And lastly, we're going to have a fraction that has the denominator x minus 1. Now, in each of these cases, the denominator is a linear factor, a linear function. And so the degree of the numerator will be 1 less, which means the degree of the numerator is going to have to be 0, which means in each case, the numerator is just a number, a constant. Okay, now that we have that done, we're going to multiply both sides by this denominator. And of course, when we multiply the left side by the denominator, we get 3x squared minus 7x minus 2. Now, I'm not going to show the multiplication. What I'm going to do is think about now when I multiply this denominator with this fraction, I'm going to have a cancellation of x's, but that's all. The x plus 1 and the x minus 1 won't cancel, and I'll still have times an a. And likewise here, on the second fraction, when I multiply the denominator, x times x plus 1 times x minus 1, with the fraction b over x plus 1, the x plus 1s are going to cancel. And so I'm going to have left an x and an x minus 1 factor and times the b that's in the numerator. And then likewise on this last fraction, when I multiply both sides by x times x plus 1 times x minus 1, we'll have the x minus 1s cancel, but not the x or the x plus 1 factor will cancel. And so that will be times the c. Now, we have quite a bit of little work to do here before we're ready to get down to the nitty-gritty. And that is, we need to multiply out this x plus 1 times x minus 1. We'll get x squared minus 1 times our a. And then we need to multiply this x times x minus 1 out. We'll get x squared minus x times a b. And then likewise over here with the last term, we'll have an x squared plus an x times a c. Now we're going to multiply the a's and the b's and the c's out and gather terms. So I got a little cramp, so let me kind of skip down here a line. In this first expression, we'll have an a times an x squared minus an a times a 1. In the second case, we'll have b times an x squared minus a b times an x times b. And in the third case, we'll have a c times an x squared plus a c times an x. Okay, we continue. Now, we have three terms involving x squared. So we combine them by adding their coefficients. And the coefficients are a plus a b plus a c. That's the coefficient of x squared. Now I'm looking at the terms that involve x. And the term right here doesn't involve x, but we have a minus bx and a plus cx. So we'll add the coefficient negative b with the coefficient c, and that becomes the new coefficient of x. And then lastly, and I'm always going to have pluses in between these, there's one term that doesn't involve x at all, and it's that minus a. And so that ends up being the constant term. And so now we just compare coefficients on the left with coefficients on the right. So in the first case, we get the coefficient a plus b plus c has to be 3 because they're both coefficients of x squared. And we get the negative b plus c must be equal to negative 7 because they're both coefficients of x. And finally, we get a negative a is equal to negative 2 because the coefficient of the constant on the left side and the constant on the right side. Left side is negative 2, the right side is negative a. So we now have a system of 3 different equations, but we have 3 different unknowns. And the first thing I would do is that I would substitute in, I would multiply both sides by negative 1 in this bottom equation and determine that a is equal to 2. Now, I haven't changed anything here in that second equation, but if I know a is 2, the very first equation would be 2 plus b plus c is equal to 3. And so this would turn into, we already know a, don't we? This would turn into b plus c is equal to 1, wouldn't we, when we subtract 2 on both sides. And we also have negative b plus c is equal to negative 7. And one method of solving systems of equations is by eliminating a variable by adding the equations together. And I know you've seen this before. If we add these 2 equations together, we'll get 0b, but we'll get 2c is equal to negative 6. And so from there we can solve and get c is equal to negative 3. So the last thing we need to do then is to calculate the b value. And of course, we could use either this equation or this equation to calculate the b value now that we know c. So if we take that equation b plus c is equal to 1 and put a negative 3 in the place of c, then we would have b is equal to 4, wouldn't we? And so now we're ready for our decomposition because we know the form and we've found all of the numerators. Just rewrite the original fraction we're decomposing. So we have a over x, and a is 2, so we'll have a 2 over x plus b over x plus 1, and since b is 4, that's 4 over x plus 1. And then we have plus c over x minus 1, but since c is negative, I could say minus 3 over x minus 1. If we were to turn around and add those three fractions together, we would get the original left side. Okay, and so we have done the decomposition. Okay, well let's look at another example here, and a couple more examples, and then we'll move on. Okay, we're to decompose 4x squared minus 1 over 2x times x plus 1, the quantity squared. And you see here the denominator is actually already in factored form. So we've got that step out of the way, fortunately. Now the next thing is to determine the format of the decomposition. And if you'll notice here, since it's already in factored form, we have the factor 2x, and we have the factor x plus 1. But the factor x plus 1 is repeated twice. So that's the reason for the square. And so this is that repeated linear factor idea. We're actually going to have three different fractions to decompose. One of them will have the denominator 2x. The next one will have the denominator x plus 1 to the first power. And we have one more in this case, and that will have the denominator of x plus 1 to the second power. If that would have been x plus 1 to the third power, we'd have one more fraction here. Okay. Now in each of these cases, the denominator is a linear function. So in each of these cases, the numerator is just a constant. Even in this last fraction, the factor of the denominator is x plus 1, the factor we're talking about. Although it's squared, the factor is x plus 1, which is linear. Okay. Well, now we know what it's going to look like when we're done. We just have to calculate a, b, and c. So we'll multiply both sides by 2x times x plus 1 squared. And that will leave on the left side then 4x squared minus 1 alone, because the whole denominator is canceled. But when we multiply this first fraction, only the 2x will cancel. We'll still have an x plus 1 squared times an a. And when we multiply with the second fraction, the 2x won't cancel. One x plus 1 factor will cancel. So we'll have 2x and an x plus 1 to the first power left over, and that's times a b. And then in this last fraction, the 2x won't cancel, but the x plus 1 squared will. So we'll have a 2x times a c. And then we continue kind of like we did before. We would multiply this out. We'd get x squared plus 2x plus 1 times a. We'd multiply out here, we'd get 2x squared plus 2x times a b. And of course here we have 2x times a c. And then we continue. We'll multiply the a out, we'll have an a times an x squared, and then an a times a 2x. Now it's going to be convenient to write that as 2ax so that we can see the coefficient is 2a. Plus an a times a 1. When we multiply the b out, we'll have a 2bx squared plus a 2bx. And in the last case, I'm going to rearrange that. 2 times x times c is nothing more than 2cx. And then we gather terms. So let's see, we only have two terms involving x squared. The coefficient of a and the coefficient of 2b. So we add those together, a plus 2b times x squared. We have three terms that involve x to the first power. So we add those three coefficients together, a 2a plus a 2b plus a 2c. And that's the new coefficient of x. And I see we have only one term left over that doesn't involve x at all, and that's just a, so plus a. Now, once again, what we end up doing is we go through the process of comparing coefficients. On the left side, the coefficient of x squared is 4, and on the right side, it's a plus 2b. So that tells us that a plus 2b must be equal to 4. On the left side, there's no x to the first power, is there? On the right side, there is. That is, the coefficient 2a plus 2b plus 2c must be 0, because we're not really allowed to have any x's over there since there aren't on the left, right? So 2a plus 2b plus 2c has got to be equal to 0. And finally, the constant a has to equate to the constant on the left side, -1. Well, what we could do right away, I'm seeing here, is we could combine these two. If a is -1, then on top it ends up being a -1 plus 2b is equal to 4. And we ought to be able to do some calculations there and figure out that b is equal to 5 over 2. Oh, Okay, now we could take that middle equation. Okay, so we know the b value and we know the a value. So in that middle equation, we've got 2 times a, which is -1, plus 2 times b, which is 5 over 2, plus 2 times c has to be 0. And so we ought to be able to solve for c. This is what, -2 plus 5 plus 2c is 0. And so I think we get 2c is -3, so c is -3 over 2. Now, okay, so we know our a, b, and c values. Let me make sure I haven't made any kind of error. I think we're good here. I'm working blind. I don't really know what the correct answer is, but I feel confident that we've done it correctly, so we'll go ahead now. So our decomposition looks like this. It's a over 2x, and a is a -1. And so we could say it's the negative of the fraction 1 over 2x, plus b over x plus 1. Well, b is 5 over 2, divided by, of course, x plus 1 for that middle term. And then finally, plus c over x plus 1 squared. But c is a negative number, so I could write it as -3 over 2 times x plus 1 squared. Now, when we actually use this in calculus, this form would be all right. But if I was wanting it to look better, I would do a little bit of changing here in this second fraction. Let me tell you what I'm doing. I'm thinking of 5 over 2 times 1 over x plus 1. That's the way I'm thinking about that. If I took 5 over 2 and multiplied with the fraction x over 1, I could say 5 over 2 times the numerator divided by x plus 1, which is what I have. But it looks better if I'd say 5 over 2 times x plus 1. That looks a little better. So I'm going to change this middle fraction to 5 over 2 times x plus 1. And likewise, I'm going to change this third fraction to 3 over 2 times x plus 1 squared. And I prefer that look. The top look is a little clumsy looking, but it would be useful even when we start using these for a calculus purpose. Okay, so we've seen linear factors, we've seen repeated linear factors. Let's look at a situation where we have an irreducible quadratic factor. Okay, here we're to decompose x squared minus 1 over x cubed plus x. We take a quick look, and yes, we're assured in this case that it is a proper fraction, so we can decompose. So the next thing we do is we factor the denominator. Now remember, we don't care about, although we can factor the numerator, that's counterproductive for us. That won't help us. In fact, it will make things worse for us. So when I factor that denominator, I'll have x times x squared plus 1. And I can't factor x squared plus 1 any further without taking extraordinary measures, and it won't factor using rational numbers only, whole numbers or fractions. So that's an irreducible quadratic. That's the deal there. That is an irreducible quadratic. Okay. So, oops. In this case, we only have two factors in the denominator, x and x squared plus 1. So all we have to worry about is what are those numerators going to look like? Well, in the first fraction, the denominator is x, that's linear. The numerator is just a constant. In the second fraction, the denominator is quadratic, so the numerator has to be to the first power, has a first power. So it means it has an x to the first in it. So it could be some constant times x plus some constant. So we write it in that fashion. Now we know the look. So we'll multiply both sides by the expression x times x squared plus 1. And when we do, on the left side, we're left with just x squared minus 1. On the right, when we multiply the first fraction, the x's will cancel. We're left with x squared plus 1 times an a. In the on the second fraction on the right, the x squared plus 1 will cancel. So we're left simply with an x times the numerator of bx plus c. And then we begin to kind of clean up and rearrange. A times x squared we'll write as ax squared, plus a times 1 we'll write as a. Over here, x times bx, of course, we'll write as b times x squared, and then plus x times c we'll write as cx. And then we combine our like terms. We have an a plus b times x squared. We have plus a c times x. We have plus just an a alone. When we compare the x squared coefficients, we know that a plus b must be 1, since that's the coefficient on the left side. When we compare the x to the first coefficient, since there's no x to the first on the left, the c must be 0. And once again, we're kind of fortunate here that a is negative 1. Okay, a is the constant, and it's negative 1 on the left side. Well, then it's pretty easy. And sometimes this is a little more difficult than what we're coming up with right now. I'm giving you some ideas. But now we know the a value and the c value. The only thing left to know is the b value. So in that first equation, we put the a value of negative 1 in for a and solve for b, and we get b is 2. So our decomposition is of this form: x squared minus 1 divided by x times x squared plus 1 is equal to a over x, negative 1 over x, plus bx plus c, that's over x squared plus 1. Well, the b is 1. The c is 0. So we have 1x plus 0, or just x, over x squared plus 1, and we have our decomposition.
I'm sure you caught my error here. Unfortunately, I can't fix it, but there should be a 2x. B is 2, not 1. So right here, of course, we should have 2x instead of x. I apologize for that error.
Okay, on the next page, we've gone through the proper procedure for doing these. On the next page, I want to show you a little shortcut that sometimes will help and sometimes it won't. And I'm not going to expand on it much more than this, because we've been doing this the proper way. What I'd like to do is go back to the very first problem that we worked on to decompose and show you a shortcut. As you can see, I said that sometimes works. And many times it will, but there are times when it won't, and so we need to be prepared to do as we have been doing, because it will always work. So if you recall, here's what we did. We factored the denominator, and that's once we did, we figured out the form of the decomposition. And then we multiplied both sides by x plus 1 times x minus 4, and we got to the stage that you see right here. Now, what we did previously is we multiplied the A and the B out, and we combined terms and so on, and compared the left and to the right. Here is the alternative method, is we stop right here and do something different. Now, let me remind you that we're trying to find, well, let me first remind you that the left side and the right side are equal. Okay, so we just don't know what A and B are yet. Okay, but they're equal no matter what x values that we have. And so if we're wanting to find A, see, I'm thinking, you know, if I want to find A, then it would be nice to make B go away. I'm not using very precise math language here. And the way I could make B go away is I could choose an appropriate x. See, if I choose x, remember, because the two sides are equal for whatever x values we have. So if I choose x to be -1, then you see in front of that b, I'll have a 0 times b. Okay, well, then that would be only a left that I didn't know. So I could put a -1 in for all of my x's, and I'd have 3 times -1 on the left side, minus 37. Remember, x is -1. And on the right side, I'd have x minus 4 times a, but x is -1, so it'd be -1 minus 4 times a, plus my x plus 1 times b. Well, since x is -1, that's -1 plus 1 times b. And the whole purpose of what I was doing is that becomes 0, doesn't it? And so what I'm left with is -3 minus 37, or -40 on the left side, times and a -5 times a on the right. And so I have a is -40 divided by -5, which is +8. And that's what we found before. Now, if I want to find b, then it would be nice to make the a go away. Which that means I need to choose an appropriate value of x so that x minus 4 ends up being 0. And then I have 0 times a. So I'm going to choose x in this case to be +4. So when I substitute 4 in for all of my x's in this equation right here, that's what I'm talking about, I'll have a 3 times a 4, 3 times x minus 37, is equal to x minus 4. But since x is 4, that's 4 minus 4 times an a, plus x plus 1 times b, that'll be 4 plus 1 times b. And on the left side, I have 12 minus 37. I started to do that in my head, but I decided I better be careful. Here we have 0 times a, and here we have, of course, just a 5 times b. Well, 12 minus 37 is -25, isn't it? And so I get b is -25 divided by +5, which is -5, and that's the value we got previously. Like I said, there's a little shortcut that sometimes works. It won't work in all cases, but in many cases it will. Well, that's the end of the process of decomposition. Of course, that's something you'll need to practice, and then we'll move on to other things.